semester is actually to run out of room on Canvas again. That's my goal this
Wait,
semester.
when did you run out of room on Canvas?
I don't think you will. Was that your
Finals
goal
week.
last semester?
No, it just happened.
I don't think you will. Because you have like more days.
How good is it? How good?
Per lesson.
That's true. I don't think I will either.
Unless you throw a bunch of like mini lessons with tons of like stuff.
Second in the 200? No, third in the 200.
Okay, so you guys actually went ahead and started this yesterday when I signed you the trig ratios, Khan Academy stuff. So it should have been review. Should have been SOHCAHTOA if you guys remember that. So you guys did triangle ratios with sine, cosine, and tangent. Was there also secant, cosecant, and cotangent in that as well?
No.
Okay. Fun. So as a brief review of that, of course, we're going to start with trig functions on acute angles. When I'm talking about trig functions on acute angles in a right triangle, we have specific names for the sides of a right triangle in regards to that specific acute angle theta. So wherever our angle is, angle, wherever our theta angle is, will determine what the sides of this triangle are labeled. So the one that never changes is the hypotenuse of my triangle, because that's always the diagonal across from our 90-degree angle. Our two other sides are going to be opposite and adjacent. As you can probably guess, the opposite side is the side opposite my angle theta. And the adjacent side is the side that touches my angle theta. The position where theta is determines which side is opposite and which side is adjacent. So for example, if I had the same triangle, but I made my other acute angle my theta, that's going to change where my opposite and adjacent are. So again, my hypotenuse is the diagonal. My opposite side then would be the bottom leg, because that's the one that is opposite my angle theta. And then my adjacent side would be this right-hand leg, because it is the side that touches my angle theta. So those two will change depending on which angle we identify or you identify as theta. Everyone okay with that? Which angle never, or which side never changes? Hypotenuse. It's always the side across from our 90-degree angle. Okay? So now that we have that written down, let's go ahead and identify the ratios associated with each of our trig functions. So the three that you are used to are sine, cosine, and tangent. As a review from yesterday, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Everyone okay with that? If you ever can't remember those main three trig functions and which sides they correlate to, they do have the fun saying SOHCAHTOA. Which breaks it down. So sine is O over H, which is opposite over hypotenuse. Cosine is A over H, which is adjacent over hypotenuse. And tangent is O over A, which is opposite over adjacent. So that's another good way to remember that. So I called these the main three trig functions. That is because there are three others that we're also going to start dealing with here in trigonometry. The first one is called cosecant, and it is CSC. It is the opposite of sine. So sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. Cosine also has this opposite or reciprocal trig function, and that is called secant, which is SEC, and it is hypotenuse over adjacent. So it's cosine's ratio just flipped over. And then tangent also has a reciprocal trig function, which is called cotangent, and it is adjacent over opposite. So these three are new to you. There's no fun saying for how to remember these. You're actually going to make one up at some point. We're just not there yet. Does everybody have those written down? Does everyone see how the three over here are reciprocals of the three over here? So they're the ratios that are associated with our main trig functions just flipped over. That's going to be important. Make sure everybody's done writing. Okay, so I called these three reciprocals of these three, which means that there's a certain relationship or way that I can write these out in terms of their reciprocal function. So we're going to call these the reciprocal identities. And you're going to come to love these. If not, you need to pretend like you do because they're going to be everywhere. So the reciprocal of sine is 1 over, oh gosh, sorry. So sine is the same as 1 over cosecant because cosecant is the reciprocal of sine, which means that cosecant is equal to 1 over sine. Cosine is 1 over secant because secant and cosine are reciprocals of each other, which means secant is 1 over cosine. And then tangent is 1 over cotangent because tangent and cotangent are reciprocals, which means cotangent is 1 over tangent. I want you to star these or circle these or box these in because these are going to have to be in your brain at some point. Okay, I'm not saying you have to memorize them today, but you will want to in the near future.
That's my niece too. That one is a part of it.
No, please don't tattoo any sort of math, anything on your bodies.
But I have to like, what if I did it on like my hand?
No.
But I have to like, run, like
You'd have to cover it up for a test.
What? No.
Why?
Because that's cheating.
How is it cheating if you
I love it so much.
It's a form of artwork. How is it cheating?
You just love them.
You just love them so much.
Yeah.
That's not in the syllabus.
Math cannot be
No, I mean-
represented anywhere but on your cheat sheet or what I provide on the board. There we go. I laid it out for you.
What's provided on the board, I wrote it on my
Syllabus.
So I need to put in there about
What if
tattoos.
someone tattooed like 2
I mean,
plus
if you want
2
us to,
on their arm?
That's cheating.
Yeah, because like that's
Yes.
something that everybody should know.
Keyword
Knowledge.
should.
Ha, ha, ha.
Tell us
Should.
also thought we should know how many feet are a mile.
Whatever, I'm getting the sign saying.
Okay. Does everybody have these reciprocal identities written down? Fantastic. Let's go ahead and solve a problem with them. Because I know it's just so much fun.
Whenever we like combine this stuff, do you want like a reduced fraction or like
Yes.
you don't want the actual answer? Yeah.
Say that again. What do you mean by actual answer
Like
rather than
when we do
reduced
like
fraction?
tangent.
Okay.
Of data. Do you want the actual answer or like do you want just like the reduced number?
I guess I'm confused by what you are determining is the actual
Okay,
answer
just-
and what you're
do you-
determining
just
is
do
You want
the.
the fraction, like you have the cosine up there, or do you want us to solve the fraction?
Oh gosh, we don't do decimals in here. If that's what you're asking.
Yeah.
We don't do decimals in here unless I say that we can.
So,
I'm anticipating that this will be a 2 to 3 day lesson, so we're not going to get through all the notes today. Just I'd leave that out there.
Darn.
like 3 days counting yesterday or 3 days counting like.
Today, when I'm actually in front of you to teach it. Yes, yes, there is.
I don't know, there is. I don't know what you were thinking. I don't know, you were celebrating.
Okay, so this problem says if theta is an acute angle and cosine of theta is equal to 3/4, find the values of the trigonometric functions of theta. So that means I want to find all 6 of those trig functions solved for theta. Wait until everybody's done writing. Okay, so when I'm solving something like this, the first thing I need to do is I need to draw the shape that we're working with. So here, that's a right triangle. So I drew my right triangle, I put my 90-degree angle to make it a right triangle. I have a question for you. I can't do anything until theta has been assigned, which means I need to pick which one of these 2 acute angles I'm going to use as my theta. Does it matter which one I choose? No, it does not. Because where I put theta will assign specific side lengths to the appropriate side. So it doesn't matter which one I pick to be my theta, because it's going to work out the same either way. So I'm going to go ahead and, for ease, identify this bottom left acute angle as my theta. If I want to solve this triangle for all 6 of my trig functions, I have to know all 3 sides. Do I have all 3 sides right now? But I do have how many of them? 2. So I need to go to this cosine, and I need to identify which 2 sides I have been given. What is cosine? It's what over what? Adjacent over hypotenuse, which means that my adjacent side is 3, and my hypotenuse is 4. So I can go ahead and put those 2 measures down. My adjacent side will be the bottom one, because it is the side that touches my angle theta. And then 4 is going to be my hypotenuse because, well, that's the diagonal across from my 90-degree angle. Everyone okay with how I assigned those? Again, it doesn't matter which angle you choose to be theta, because you're building your triangle, assigning specific lengths to specific sides, and your ratio will still stay the same, okay? I have 2 sides. How do I find the third one? Pythagorean theorem, good. So I'm just going to say this is x for right now because I don't know. So I have x squared plus 3 squared equals 4 squared. I go ahead and square everything. I go ahead and combine like terms, and I solve for x. So when I do, I get x squared plus 9 equals 16. I subtract that over, and I get x squared equals 7. Right, because 16 minus 9 is 7. What do I do now if I want x by itself? Square root it, and I get x equals plus and minus the square root of 7. Uh-oh, I got 2 answers. Why does it have to be positive? Because you can't have a negative length. You will be amazed at how many times Sony messes that part up. So that means x has to be positive square root of 7, and I want it left as the square root of 7 because that is an exact answer, not a rounded decimal. As Mr. Flora would say, we are building cabinets here. Okay? Exact values only.
All I see is a 2D board.
So now my 3 side lengths are 3, square root of 7, and 4. Are we all okay with how we got there? So what am I going to do now? Solve for the rest of my trig functions. So I'm going to go ahead and erase this because, well, it's in my way. When I say solve for the rest of my trig functions, that means sine, cosine, tangent, cosecant, secant, and cotangent. So I like to write all of those out first, starting with my main three ones, sine, cosine, and tangent. Okay. Say that again, Colin.
Find it.
No, because we already know what it is. We already have one of the 6 done. Right? So we know cosine is 3 over 4. What is sine going to be then?
No.
Square root 7 over 7.
Square root of 7 over 4. What is tangent going to be?
Square root 7 over 3.
Square root of 7 over 3 because it is opposite over adjacent. Using this information, I would like you to find the next 3 trig functions. So cosecant, secant, and cotangent. Marissa, did you have to do a whole lot of work to find cosecant, secant, and cotangent? Why not? We just flipped the original 3 fractions.
Wait.
So cosecant is going to be 4 over the square root of 7. Secant is going to be 4 over 3. And cotangent is going to be 3 over the square root of 7.
Where's leaving it as square root 7? She didn't say that.
We are leaving the square root of 7 in the problem, yes.
No.
We're
However,
not getting rid of it because it's a rational number.
Don't rationalize.
Yeah.
say it again, say it again, say it again.
That's what I was thinking.
We never leave a radical in the denominator. So for cosecant and cotangent, I need to rationalize these fractions. I'm going to go ahead and rewrite it so that we can more easily see what we're doing. So if I have 4 over root 7 and I want to rationalize this, what am I going to multiply the top and bottom by? Square root of 7. When I do, I'm left with 4 root 7 over 7, and that is perfectly fine. We always rationalize when a radical is in my denominator. Always, always, always. Yes,
The square root 7 up there is still a radical.
Gotta keep it.
but it's in the numerator.
Oh, okay.
It's not in my denominator anymore,
Okay.
and that's all I wanted. So then we're going to do the same thing with my cotangent of theta, because I got 3 over root 7. So when I rationalize, what does that become?
I can't say.
3 root 7 over 7. Make sure if you can reduce, you do. We can't here because 3 and 7 are prime. But if you can, you should. Questions, concerns, or issues with that? I'm going to give you a second to finish writing and processing what we just did, and then we'll move on. Ismail.
So we only need to put our radicals in the numerator, but does that affect sine, cosine, and tangent?
No, because it only had radicals in the numerator. If I had a radical in the denominator on any of these, I would have to do the same thing.
Okay.
It doesn't matter which trig function I'm using. If I end up with a radical in the denominator, I have to rationalize. Questions, concerns, or issues with that? Is every single right triangle the same, or do we have some special kinds? We actually have 2 special kinds of right triangles. And these special kinds are special because they have a special relationship between their angle measures. So in a second, once I'm sure that everybody's done writing, we'll go ahead and we will identify those special right triangles and the trig functions associated with them.
It's like the 3069 thing that you found my school.
30, 60, 90, and 45, 45, 90 are our 2 special right triangles. Cody, are you writing off the notes right now? 4. Okay. So I'm going to go ahead and I'll work slowly, I promise. You can catch back up. But okay, so the first special right triangle we're going to identify is our 45, 45, 90. Definitely not drawn to scale. Okay, So on a 45, 45, 90 degree triangle, my two acute angles are both 45 degrees, and of course my right angle is 90 degrees. Because both of my acute angles are 45, what do I know about the sides across from them? They're also the same, right? So in a 45, 45, 90 degree triangle, we actually have a special relationship between the side measures that was found using the Pythagorean theorem, but we don't need to do it because this is a common one we're going to use. And that is that whatever the length of each of my short legs are, here we're assuming they're 1, my hypotenuse is the square root of 2 times that side length. We're assuming that our short leg is 1 because we're actually going to be using this to build our unit circle. And on a unit circle, it's always 1. Okay? So knowing that my side lengths are 1, 1, and the square root of 2, I would like for you to build my 6 trig functions using these sides. Okay, so I want sine of 45 degrees, I want cosine of 45 degrees, and I want tangent of 45 degrees, and then I want cosecant, secant, and cotangent as well. Does it matter which of those 45 degree angles I use? No, because they are the same, their sides are the same, which means my ratios are going to be the same. So I want all six trig functions solved for a 45 degree angle.
So we're at 45% bigger this time?
Yes, because I know what my angle measure is.
Okay.
Okay, so these are the 6 trig ratios that I got for this 45, 45, 90 degree triangle. If any of yours are different, please let me know. So sine, I got 1 over the square root of 2, which we rationalized to be root 2 over 2. Cosine, also root 2 over 2. Tangent then is equal to 1. Cosecant is square root of 2. Secant, square root of 2. And cotangent is 1. Anybody have any major issues with that? Yes.
So the COB45 is the 1 over square root of 2. Put square root
For this one?
of 1.
Okay, so cotangent is adjacent over opposite. So from 45 degrees, my adjacent is 1 and my opposite is 1. So I'm not really sure. It's really easy to mess this up. So it's really easy to throw an extra side in there or just identify the wrong side, and that's okay. It happens. So just go back and recheck it. Even I do it sometimes on accident. Questions, concerns, or issues with that 45, 45, 90 triangle? Okay, we're going to do the same thing with my 30, 60, 90 degree triangle once we identify those special angle measures. I'll leave that up while I draw our 30, 60, 90 degree triangle to the best of my abilities. Okay. So here I have a 30, 60, 90 degree triangle. The important thing you need to remember here, in case you're asked to assign angles to specific sides, is that if I know it's a 30, 60, 90, oh my gosh. Obviously the right angle, so the one across from the diagonals are 90-degree angle. The angle across from my shortest leg is my 30-degree angle, and the angle across from my largest leg is my 60-degree angle. So small angles correlate to small sides, larger angles correlate to larger sides, opposite them, okay? So that's in case you ever need to fill it in on your own. So for this one, we're actually going to be doing two sets of trig functions once we identify these sides, one for the 30-degree angle and one for the 60-degree angle, okay? So the side relationship on a 30, 60, 90-degree triangle is that assuming my shorter leg is 1, my longer leg is the square root of 3 times that side, and my hypotenuse is 2 times that side. So our side measures on a 30, 60, 90 degree triangle, assuming our short leg is 1, are 2, root 3, and 1. So having this information, I want all 6 trig functions in terms of my 30-degree angle. So you're finding sine of 30, cosine of 30, tangent of 30, and so on. Gabe, go ahead and give me all of these trig functions in terms of the 30-degree angle.
Sine is 1/2. Cosine is square root of 3 over 2. Tangent is square root of 3 over 3. Cosecant is 2. Secant is 2 square root of 3 over 3. Tangent is square root of 3.
Good. Anybody get anything different for those 6 trig functions? Okay, I want you to repeat this now for our 60-degree angle.
Can I just think about it in my head?
No. You're going to want these written down. You can squeeze it on the side, I'm sure, Gabe.
Must be ordered.
Cosine tangent of 30, how's it 33?
For cosine of 30, so it's adjacent over hypotenuse. So from our 30-degree angle, my adjacent side is root 3, hypotenuse is 2.
The COT side.
Oh, cotangent, okay. So it's adjacent over opposite. So it's going to be the square root of 3 over 1, which is just the square root of 3. Molly, go ahead and read me off your trig ratios.
Okay. Square root of 3 over 2. 1/2. Square square root of 3. 2 times the square root of 3 over 3. 2 and the square root of 3 over 3.
Anybody have any major questions, concerns, or issues with identifying the trig ratios for these special right triangle angles? We're okay? So of course, we're gonna go ahead and do an example next, because why not?
Oh, 30 degrees.
30 degrees, yeah. Okay, so the problem says, a surveyor observes that at a point A located on level ground, a distance of 25 feet from the base B of a flagpole, the angle between the ground and the top of the pole is 30 degrees. It asks us to use this information to approximate the height h of the pole to the nearest tenth of a foot. So we are actually going to do this two ways. One with no calculator and one with a basic calculator and one with a scientific or graphing calculator, okay? So the first thing we're going to do whenever we're presented with a problem like this is what? Draw a picture. Always works. Always, always. So I have a flagpole over here that intersects the ground at point B. I have point A over here, which I believe is where the surveyor is pretty much standing. And I know that this side is a flagpole. The angle then between the ground and the top of the flagpole, this distance away, is 30 degrees. And I also know that my surveyor is 25 feet from the base of the flagpole. It asks me then to solve for the height of that flagpole h. Okay, so I drew a pretty picture. As I'm looking at this, my first instinct is probably to use the Pythagorean theorem because I'm missing a side to a right triangle. But I can't do that because I don't have two sides to work with. So I'm going to have to find some alternative way of dealing with this, which to us means I'm probably going to use a trig function because that's what I just learned and is kind of a shortcut for Pythagorean theorem sometimes. But the key here is I have to pick the right trig function to use. So in regards to this 30-degree angle, Which two sides do I know or are solving for here?
Opposite.
Opposite and adjacent. So I have two trig functions that deal with opposite and adjacent sides together. What are they?
Tangent and cotangent.
Tangent and cotangent. So I don't like to use the reciprocal ones if I don't have to, which is the cosecant, secant, and cotangent, because they don't exist on a calculator, which means I'm going to go ahead and I'm going to use tangent of that 30 degrees. Okay, because that's one of my main ones, which means I'm going to use it more. In regards to this 30-degree angle, tangent is opposite over adjacent. My opposite side is h, and my adjacent side is 25. Right? We're all okay with that. So from here, there are two ways to solve it. So I'm going to draw a line so that I can show you the two ways. The first way we're going to solve it is using exact values. So those values we just figured out from our special right triangles. My goal here is to isolate the h, so I'm going to go ahead and multiply that 25 across. And when I do, I get that h is equal to 25 times tangent of 30 degrees. I can't really do anything else here until I know what tangent of 30 degrees is. So I'm going to go back to those special right triangles that we wrote down, and I'm going to find what the value of tangent of 30 was. So what is it? Is it just the square root of 3? Square root of 3 over 3, right? Everybody see that? Tangent of 30 degrees should be square root of 3 over 3.
Oh.
Yeah, see, we already did all the work for that. So then this height becomes 25 times the square root of 3 over 3. If I were to simplify this, that means that h is 25 times the square root of 3 divided by 3, and I can put that into a calculator to approximate it. Right? So do that. Find out what 25 times the square root of 3 divided by 3 is. Because it wants it to the nearest tenth of a foot. If you're using one of the little yellow calculators, make sure you change the mode on it to classic. So you just hit the mode button and go down to like the third row. And you'll click classic. Okay, what do we come up with?
Oh, hold on. I know I did it wrong.
Okay, so we got that h is approximately 14.4 feet. Are we okay with that? So now we're going to do it the total calculator way. Okay? First thing I'm going to need you to do is check the mode on your graphing calculator or whatever calculator that you're using. Okay? My angles here are measured in what? Degrees. So I need to make sure that my calculator is in degree mode. Once you think you have it, check with the person sitting next to you. Make sure their calculators are in degree mode. If they're not, we will get a wrong answer because I'm inputting degrees here. Are we all good? Okay. So what we're going to do now is we're going to use the same problem, but we're going to solve it only with a calculator. Okay, so we're not going to have any fractions in here anywhere. So I still have tangent of 30 is equal to h over 25, right? And I still need to, I still know to isolate the h, I need to multiply the 25 over. So I get 25 times tangent of 30 degrees equals h. I can put that directly into my calculator because all of your calculators have a tangent. And you're going to put it in just like normal. You do 25 times, then you're going to hit that tangent button, and you're going to type in 30 because my angle measure here was 30 degrees. What did we get?
14.4.
Good, it checked out.
I like that way.
Well, you all like that way better. However, we know that Mrs. Duran does a no calculator portion to all of your tests. So we should also know this way,
Practice it.
okay? Well, no, but you could have left it here. That would have been okay.
Oh, really?
Wait, oh, it doesn't do
all
that?
like 18 of the things.
That's you assuming there's only 18 of them.
What?
We're gonna do something which will make it easier. What's your question?
So you said to the nearest tenth, but you said we could also leave it like that.
So if you were doing a no calculator, you would leave it as the fraction. Or if I said I wanted exact values, you would leave it as the fraction.
Well, just because
Okay,
I
so-
said it doesn't, if I didn't say it, that means we're gonna have to do it anyway. But now we're
have to worry about it.
Okay, is everybody okay with how we did this?
Yeah.
Ismail, what's your question, honey?
So on the homework, it says nearest tenth of a foot, use a calculator and get it to that.
Yes. But if I gave you like a no calculator portion, you would have stopped here at the fraction 25 root 3 over 3. Because there's no way you guys could have simplified that easy enough and in the amount of time I give you. So that would be an acceptable answer.
I have okay.
Okay, are we all good to move on? I don't know how much time we have. Oh, we have 8 minutes, plenty. Okay. We are not going to do anything crazy now. We're just going to write the identities and we will use them next class. Okay?
I guess.
So these are something you're definitely going to want to star or circle or box in, indicating that you're going to need to memorize them. And they're definitely good things to put on your first cheat sheet when I give you a quiz. Okay? We're going to start with all of our fundamental identities. My first set of fundamental identities are our reciprocal identities, which we kind of already covered, which is awesome. Our reciprocal identities are that cosecant of theta is equal to 1 over sine of theta. Similarly, sine is equal to 1 over cosine. Secant is equal to 1 over cosine. And cotangent is 1 over tangent. Of course, we can write the reciprocals going the other direction as well. It might not be a bad idea. So sine is 1 over cosecant. Cosine is 1 over secant. And tangent is 1 over cotangent. Those are our reciprocal identities. We already identified what they were and wrote them down in our notes, but I like to put all of our identities in the same place so it makes it a lot easier to go back and find them. So those are our reciprocal identities. The next identities we have are the tangent and cotangent identities. The first of these is that tangent is equal to sine over cosine. Cotangent then, because it's just tangent flipped, is equal to cosine over sine. So those are your tangent and cotangent identities. And then the last ones are called the Pythagorean identities. These are my favorite. So the first one is that sine squared theta plus cosine squared theta equals 1. My second one is that 1 plus tangent squared theta equals secant squared theta. And then my third one is that 1 plus cotangent squared theta equals cosecant squared theta. So these are your 3 Pythagorean identities. Again, all of these identities at some point are going to have to be memorized. Yes. There's one, yes, Mallory, sorry. Yeah, of course. Sorry, dear. that high enough? Okay. There's one more thing I want to point out, but we're not going to do any more work today. Okay, we're going to stop here. It's a perfect place to stop. Tomorrow, we're going to start with some proofs, and then we're going to start with some trigonometric identities and proving them or disproving them. Okay? So in these Pythagorean identities, I don't just have sine, cosine, tangent, cosecant, secant, or cotangent, right? I have sine squared, or I have cosine squared, or I have secant squared. So when we have a trig function squared, we need to know what that means in terms of that trig function in general, okay? So when we see, I don't know, for example, cosine squared theta, this is the same as my entire cosine of theta squared, which of course can be rewritten as cosine of theta times cosine of theta. Okay, so it separates a very particular way. We're not squaring the angle, we're squaring the entire trig function solved at that angle. Same thing if I had a cosine cubed or a cosine to the fourth or a cosine to the fifth. That indicates that I'm taking that whole cosine of that angle and taking that answer to that specific power. It also indicates how many times I'm multiplying that trig function by itself. No different than having x squared or y to the third. It indicates that we multiplied it by itself that many times. Okay, so make sure you understand that this square does not go directly to the angle. It applies to the entire trig function at that angle. Because that's also another huge issue that I see. Last question before I officially set you loose. Can I take a trig function of a 90-degree angle?
There's no one.
Yes or no? I want you all to think about it for a second. So for example, if I had this awesome, beautiful triangle, and I was calling this angle C, and I wanted to take sine of angle C, could I do that? Why not?
Because the hypotenuse and opposite are the same thing.
Okay, so I have no idea which one of these is my adjacent side because I have two, and my opposite is my hypotenuse, which just gets really, really confusing. You can never take a trig function for a 90-degree angle or for an obtuse angle. It only works on acute angles, okay? Please cement that somewhere in your brain. Your homework is posted on Canvas. Obviously, if you have any questions, let me know. You can do some of them right now. Some of them you can't do. So don't feel worried if you can only do like 4 of the problems, okay? Have an absolutely wonderful day.